Projectile motion. An object is moving in a projectile motion when it moves following a parabolic path or trajectory and when the air is being neglected. A parabolic path is a path that is shaped like a parabola, something that is bowl-shaped. Moreover, projectile is also defined as any object that is given an initial velocity and follows a 2D path acted upon by gravity alone. In figure 1 here, it illustrates an example of a parabolic path followed by a projectile or trajectory. It should be noted that at any point along the trajectory, the acceleration along the horizontal is zero. That is, along the horizontal, the object moves at constant velocity. It is not accelerating. On the other hand, along the y-axis or vertical, the object accelerates under the influence of gravity alone. In figure 1 here, we denoted our acceleration due to gravity as a sub y, and this is equal to negative 9.8 meters per second squared. In this module, we will again use the sign convention coupled to determine the cardinal directions east, west, north, and south, as discussed during the lesson about making free body diagrams. So we have here, to the east is positive or to the right, to the west or to the left is negative, up is our north or positive, and down south is negative. We will now derive the equations for projectile motion. To begin, we recall our sign convention. We place it here in table 3.1. We have G going up or going down. If the object is going up or going down, we have a negative sign for G. And elapsed time delta t is Tf minus T naught. For object going up, it's positive, and going down is also positive. For our velocity, the object that is going up is positive and going down is negative. And for y, object going up is positive and going down is negative. We will now derive the equations of motion along the x-axis, which is our horizontal, of a projectile. We will do this by recalling the equations of motion of an object moving with constant acceleration along the x-axis. We have presented that one explicitly in our previous lessons. Here we will be placing the subscript x to all the variables to give emphasis to the direction of motion along the x-axis. We do this because projectile motion is a two-dimensional motion in the x and y axis. So here we recall equation 3.1, 3.2, and 3.3. Notice here that these equations are the equations we have used for horizontal motion with constant acceleration and also free fall. And we have here the subscripts. And we use now the number for our equations 3.1, 3.2, and 3.3. Here we will be placing the subscript x to all the variables to give emphasis to the direction of motion along the x-axis. We do this because projectile motion is a two-dimensional motion in the x and y axis. We have equation 3.1, a sub x, open parenthesis, tf minus t naught equals v f sub x minus v naught x. 2a sub x, open parenthesis, x final minus x initial equals vf squared minus vo squared. And the third equation, final position minus initial position equals vo sub x tf minus t naught plus 1/2 a sub x tf minus t naught squared. But since an object in projectile motion is not accelerating along the x, then a sub x is equal to 0. So in projectile, a sub x is equal to 0. That's why you can see here we have the left side of 3.1 a sub x is, that's why we have here in the left side of 3.1 a sub x, this becomes 0, and in 3.2 a sub x will become 0, and in 3.3 a sub x will become 0. So we now have our equations for projectile. So the 3.1 becomes our 3.1b, and that's 0. Left side is 0 because a sub x is 0 equals vfx minus v naught x, just copy. So this is now equation 3.1.b. Then for the second equation, from 3.2, ax is 0 here on the left side of the equation. So 0 equals vf squared minus v naught squared. This is now equation 3.2.b. And for our third equation, from 3.3, the second term on the right is 0. We copy the left side, xf minus x naught equals, we only carry the first term on the right side of the equation, v naught x times tf minus t naught. From 3.1.b and 3.2.b, we now have .b. That's 0. I'm just copying it, equals v f sub x minus v naught x. So we transfer this to the left side of the equation. That's why we have v naught x is equal to vf x. So the initial velocity along the x is equal to the final velocity along the x. Also in 3.2.b, say 3.2.b, we will arrive at the same equation. We copy first 3.2.b, 0 equals vf squared x minus v naught x squared. Transfer this to the left. So v naught x squared equals, transferring negative vox squared to the left. We have positive vox squared equals VFX squared. Then simplifying by extracting the square root of the entire equation. So square root of square, that's VOX, equals square root of square, that square root over and square, that cancels, VFX. So notice that we get the same equation from 3.1 and 3.1 point B and 3.2 point B. VOX equals VFX. This means that at any point along the projectile's trajectory, the x component of the final velocity of an object is equal to the x component of its initial velocity. We now call this equation 3.1 point C. 3.1 point C. Now consider the angle alpha sub O from the horizontal to the initial velocity v naught. Then the x component of the initial velocity, can also be expressed using trigonometric function cosine as follows. We have cosine alpha naught or sub-zero equals adjacent side over hypotenuse. So we have cosine alpha O, looking at the figure, adjacent side of alpha sub O is our V naught x, not the V naught because that's the hypotenuse, the longest side of the right triangle. So it is the V naught x over hypotenuse, the V naught. And so we transpose VO to the left side of the equation, cross multiply. We have V naught x equals VO cosine alpha O. So VO cosine alpha O is equal to V naught x. This is our equation 3.1 point D. So we plug this equation 3.1 point D into our previous equation 3.1 point C. Recall 3.1 point C. V naught x equals VFX. So our equation 3.1 point C is V naught x equals VFX. Plugging 3.1 point D into 3.1 point C. So 3.1 point D V naught X into this 3.1 point C V naught X. So the left side is V naught cosine alpha O equals, copy the right side, VF sub X. This is now our equation 3.4. Moreover, from 3.3 point B, we have, so we recall our equation 3.3 point B. Let me emphasize this one because it's very important, 3.4. So moreover, you'll now get the XF by recalling from 3.3 point B, we have XF minus X naught equals VOX times TF minus T naught. Recall from 3.3 point B, XF minus X naught equals VOX times TF minus T naught. We now plug 3.1 point D into this, the V naught X of 3.3 point B. So this time, this value goes here. That's VO cosine alpha O. The VOX of 3.1 point C. So XF, just copy the left side, minus X naught equals VO cosine alpha O. And we drop now the T naught because we know that it is 0. Just copy the TF. This is now our equation 3.5. So along the x-axis of a projectile motion or trajectory, the VFX, or the final velocity along x, is V naught cosine alpha naught. And along the x-axis, XF minus X naught equals V naught cosine alpha naught T final. We will now derive the equations of motion along the y-axis or vertical of a projectile. 2.1 and 2.3. We will be placing the subscript y to all variables to give emphasis to the direction of motion along the y-axis. Moreover, we also set y naught equals 0, d naught equals 0, and write T sub f equals T. We have gt equals v sub f sub y minus v sub naught sub y. And y sub f equals v naught sub y times t plus 1/2 gt squared. We again inspect figure 3 and determine the y component of the initial velocity, or v sub o sub y. Here is figure 3 again, and we are looking at this variable v sub o sub y. Using trigonometric function sine, we have sine alpha, or angle alpha naught, equals opposite side over hypotenuse. So looking now at alpha O, opposite side is our v naught sub y, and hypotenuse is our v naught. So sine alpha O. Therefore, we transpose v naught to the left side, cross multiply, and you're left with v naught y. It's VO sine alpha O is equal to v naught sub y. We call this equation 3.1.E. Plugging this 3.1.E into 2.1, GT equals VF sub y minus V naught y. Here we plug it here, V naught y. We plug 3.1.E. So we have plugging this 3.1.E into the equation above 2.1. It was GT equals VFY minus the V naught y, which will become this, minus V naught sine alpha sub 0 or naught. Transposing the equation, because we want this one, we transpose the equation. We transfer negative V naught sine alpha naught to the left. It becomes positive. Okay, so copy GT plus V naught sine alpha naught equals VF sub y. And this is now our equation 3.6. Moreover, we now get the final y position at any point along the trajectory YF by plugging 3.1.E into equation 2.3. So 3.1.E is this V naught y equals VO sine alpha O. We plug this into 2.3. Here, we plug it into the V naught y of 2.3. 2.3 is y sub f equals v naught y t plus 1/2 gt squared. So v naught y here will become 3.1 point e. So plugging 3.1 point e into 2.3. We have, I'm copying 2.3, y sub f equals v naught y times t plus 1/2 gt squared. So the v naught y it will be placed here. VO sine alpha O is V naught Y. Thus we have YF equals VO sine alpha O. Copy the rest times time plus 1/2 gt squared. This is now our equation 3.7. Let us now write a summary of what we have derived. The position x sub f of an object traveling in a projectile motion is v naught cosine alpha naught times t. This is equation 3.5. And the y final or final position of that object is v naught sine alpha naught times time plus 1/2 gt squared. This is our equation 3.7. And the velocity v final along the x is v naught cosine alpha naught. And along the y, final velocity along the y is our gt plus v naught sine alpha naught. So this is a summary. VFX is equation 3.4 and the VFY is 3. And VFY is 3.6. Finally, using the Pythagorean Theorem, which states that the sum of the squares on the legs of a right triangle is equal to the square on the hypotenuse, we get the magnitude of the final position R of an object at any point in the projectile using the equation R is equal to square root of xf squared plus yf squared. Note that xf is drawn to the right because in our sign convention, to the right here is positive. Yf is also going up because in our sign convention, upward is positive. Then the final velocity is just v is equal to the square root of vf x squared plus vf y squared. And the direction, looking at figure 5, tangent alpha is equal to vf y over vf x. In figure 5, note that vfx is drawn to the right because our sign convention to the right is positive. Moreover, vfy is going up because in our sign convention, upward is positive. Lastly, for the horizontal range r, which is the value of xf when the object returns to the same height where it was thrown, as shown in figure 1 earlier. In other words, if an object is thrown 1 meter above the ground, then the horizontal range is the horizontal distance from this launching point to the point where the object returns to the same 1 meter height. To calculate the range, we use the equation r, range big R equals V naught cosine alpha naught times t total time of flight, where t total is equal to 2 times time to reach the highest point. From t total, we can infer that in a projectile motion, the time elapsed when the object goes up is the same as the time of going down, just like in free fall.